Side splitter theorem. So the side splitter theorem is related a little bit to, not a little bit, it's related to mid-segments. We talked about triangle mid-segments before. The side splitter theorem is kind of related to mid-segments. So what we're going to say for our theorem is a line parallel to one side of a triangle divides the other two sides proportionally. And when we say proportionally, what do we mean? They have the same. They're similar. We do end up with similar triangles. So when we say the sides are proportional, they have the same. The angles do end up being the same. But when we talk about a proportion, what are we talking about? Ratios. They have the same ratios. So the side splitter theorem gives us a way of setting up the same ratios. So let's draw a picture of what we're talking about here. Proportional, when you think proportional, you should think ratios. So here's our triangle. One side is parallel to the other side. Remember that arrows tell us when things are parallel. I'm going to call this A, B, C, D, these lengths. The length of that whole side is X, and the length of that whole side is Y. So what this says is this line divides the other two sides proportionally. So we end up with a whole lot of proportions. So when we have one segment parallel to the other side of the triangle, we can write a whole lot of proportions. I'm not going to write all of them, all the possibilities. I'm just going to write a few just to show you some of the possibilities that we can work with here. So I could say A over B, this piece to this piece, is the same ratio as those same pieces on the other side, equals D over C. So top to bottom, top to bottom. I could say A over X, this small piece to the whole side, equals this small piece to the whole side on the other side, D over Y. I could say A over D. I could compare these two across this way. Equals B over C. I can compare across this way. I could compare the lower side and the whole side, so I could say B over X, so this to the whole side, equals this to this whole side, C over X, or sorry, C over Y. I could write a lot more. So these are just a few that I can come up with. So the side splitter theorem gives us a way to write proportions based on the lengths of the sides of the triangles that we know. So let's think back for a second about when we talked about the mid-segment. Remember, the mid-segment was parallel to one side of the triangle, but where did it go on the other two sides of the triangle? What did the mid tell us about the mid-segment? Went to the middle, the midpoints of the sides of the triangle. So these two lengths were equal. These two lengths were equal. So those are our proportions there. And you remember how the mid segment compared to the base? How many times bigger was the base than the mid segment? 2 times. So those are our proportions. We get those proportions from the mid segment. So the mid segment is kind of a special case of the side splitters there, where proportions turn out really nice and even. All right, questions on how we set up the side splitters? All right, so let's take a look at a few examples using side splitter. Our key technique, the way we're going to solve problems here, is write a proportion. We just need to make sure we're writing the proportion with the right pieces of the triangle. We're comparing the same pieces as we write our proportions. So here's our first example. Start off with an easy one. Three, 9, 6, and x. And we want to find x. Well, we have a triangle. We have a segment parallel to one side of the triangle. So we know that the other sides are divided proportionally. So what proportion do we want to write here to find x? What do you think, Lee? 9 over 3 equals 6 over x. That one will work. Can we use a different one? 9 over 6 is 3 over x. That one works as well. When I cross multiply here, I get the same thing. There are a couple of other ways that I could set it up. These two are the easiest ones to set up. The others would take a little more work. So I cross multiply here. I get 9x equals 3 times 6 is 18. Divide by 9, and x equals 2. Nice and easy. Side splitter theorem, proportions, makes the proportions really easy to set up. All right, let's look at another example. So here's my triangle for this one. Here's my parallel segment. Arrows tell me that they're parallel. And I'm going to say this is 2. That whole side is x. And this is 3, and that's 4. And we want to find x. All right, so what proportion do we want to set up here? A little different than this one, but not a whole lot. Anybody have an idea? What do you think, Hershey?
3 over 4 equals x over 2.
So 3 over 4. So this is where we need to be careful. 3 over 4. So I'm using this side on the top here. So I want the one across here. So we want 2 there. But here's where we have to be careful. X is the length of this whole side. Is 4 the length of that whole side? No. This will help us though. We could say 3 over 4 is 2 over, what if we called this part y? So we could say 3 over 4 is 2 over y. And that we could find that little piece. And then we'd add those two together and we'd have the whole side. So that's one way we could do it. So 3 over 4 is a fine way to start. 2, we know that part, so we just need to make sure we have the right part in there. Anybody see another way we could set this up? Let's go with what Hunter was thinking about here. 3 over, what is the whole length of this whole side? 7. I could find the length of that whole side. 3 plus 4 equals 7. So 3 over 7 equals 2 over x. I could do it that way. So starting with what Hunter was wanting to do, 2 over x, we know 2 and we know that whole side, so we've used 3 and the other whole side. So I can do it either of these ways. So if I do it this way, I get 3x equals 14, divide by 3, and x 14 thirds is about we get 4.66 repeating. For the second time, we found the length of the whole side of the triangle. X is the length of the whole side over on this side, but we didn't have the length of this whole side yet. So in order to use x, we need to compare x. We need to compare the same things. We need to make our ratio with the corresponding parts that match. So we need to make a ratio if we're using x. We need to have that ratio be with the entire other side of the triangle. One thing you can do here, if it helps, is draw the two triangles. Just draw them separately. So you could draw the red triangle, the big triangle, and you're comparing it here to the smaller triangle, so you could separate that out and draw that triangle. So I could draw those two triangles separately, like so. I'm just going to draw them small down here. That's x, and this whole side is 7 is what we figured out. And for the smaller triangle, this is 4. And we didn't know this piece. So this is how we would make sure we're comparing the same pieces. We call that piece y. And we could go through the problem this way. We could say 3y equals 8, divide by 3, and y equals 8 divided by 3 is going to be 2.66, and then 2.66 plus 2 is 4.66. So we can do it either way. All right, other questions about this example? All right, I want to look at one more, because this one is one where students often make a mistake in setting this one up. So I want to point it out, so hopefully we don't make that mistake. I'm going to say this is 4, this is 6, this is 2, and this is x, and we want to find x. So we have our segment parallel to one side, so we know it divides the sides proportionally. So how do we want to set up a proportion here? Anybody have an idea? So let's do this. Let's do what I suggested on the last one. We're looking at, let's compare this small triangle to this big triangle. So if I break this into two pieces, I get a triangle that looks like this, 4 and 2, and my big triangle looks like this. X, how long is this big side? 10. That whole side is 10. So we can break it up into two triangles. So now this helps us out to write our proportion. Now how are we going to write our proportion for these two triangles? 4 over 10, 2 over x. That way we're comparing the right pieces. What students normally want to do here is say, 4 over 6 equals 2 over x. You want to compare this and this, and that and that. Well, the 6 isn't the length of the whole side, so we don't want to do that. So break it up into two pieces. We set it up the right way. Figure out the whole length of the side of this big triangle, the big red triangle. And now we can solve our proportion. We get 4x cross multiply equals 20. Divide by 4, and x equals 5. So this one was one where we needed to be a little bit careful. Make sure you're comparing the same parts on with each ratio. Yes.
The mid segment is half.
So the mid, if we knew that this was exactly in the middle of both sides, then it would be half. But because it's not right in the middle, then it's not exactly half. It's some other amount. Okay? All right, now we want to add a little bit to the side splitter theorem. We're going to add what we call a corollary. We've talked about corollaries before. Corollaries is something that we can figure out easily from another theorem. Our corollary says 3 or more parallel lines. Divide two intersecting transversals proportional. Sounds complicated, really not. So here are our intersecting transversals. And I'm going to do 3 parallel lines here. There are 3 parallel lines. Those are all parallel. The arrows tell us that they're parallel. And I'm going to call this A, B, call that little segment E, C, D, and F. So all we have here is, it's exactly like our triangle. Here's a base of a triangle. Here's a segment that's parallel to one side. We just added another segment in here. So we're just dividing our triangle into more pieces, is all we're doing. Nothing different here. We're just dividing the triangle into more pieces. All the sides, all the pieces are proportional. That's what our corollary tells us. So again, we get a lot of proportions that we can write. So I'm going to say some proportions. I'm not going to write them all. Some proportions. I could say A over C, this over this, equals B over D. I could say A over B, this over this, equals C over D. As long as we're writing our proportions with the matching pieces on either side, we're going to be fine. We could say A plus B, the length of this whole side, over A, equals the length of these two added together, C plus D, over C. So I'm just comparing the same pieces from side to side, writing a proportion with those pieces. There are a lot more proportions that we could write out with all the information that we have. I just wrote a few of them. So let's look at an example using this corollary. And we have one last little thing to talk about. So questions on our corollary. All we're doing is taking our triangle and adding another parallel segment or several more parallel segments. The intersecting transversals guarantee that we're going to get a triangle in here. All right. So we have this situation, and I don't want arrows. Get rid of those. And we're going to say that these segments are parallel. The arrows tell us that they're parallel. And we're going to call this X, Y, and 80 feet. And this is some fences or something on a piece of property. A crooked sidewalk maybe, 40 feet, 50 feet, and 62.5 feet. And we want to find X and Y. So we have 4 parallel lines. Here are our intersecting transversals. So our technique, our fallback method of solving problems is going to write proportions. So what proportion could we write for X, to solve for X? Wait. 40 over X, comparing those two, and we'll compare those two. 62.5 over 80. So we're just comparing writing our ratios with the corresponding pieces on both sides of our problem, and writing a proportion. Is there another way I could do it? Is there another way I could write a proportion for this? The other way I thought of was we could say X over 80 equals 40 over 62.5. And when we cross multiply, we see we get the exact same thing. So I get 62.5x when I cross multiply. 40 times 80 is 3,200. Divide by 62.5, and I get x equals 51.2 feet. So piggybacking from there, how could I write a proportion to solve for y?
80 over y over 2,
80 over y equals 62.5 over 50. So I'm using this and this. I'm going to use that piece and that piece. Works perfectly fine. Cross multiply here. 80 times 40 is 4,000. Equals 62.5 when I cross multiply times y. Divide by 62.5. And I get y equals 64 here. So just set up those two proportions, solve the proportions, and I'm set. Questions there? So side splitter, this is just an extension of side splitter. Match up your matching pieces, your equivalent pieces, your corresponding pieces. Write a proportion, solve your proportion by cross multiplying. That's kind of our big picture problem solving technique from chapter 7. All right, one last thing. Just another way to set up proportions with a triangle. Angle bisectors. So what we're going to say about the angle bisectors, angle bisector of a triangle, and what does an angle bisector do? Cuts the angle in half. So we have something that's cutting an angle in half. The angle bisector of a triangle divides the opposite side into segments. So this is kind of like what we talked about with the right triangles. Into segments proportional to the two adjacent segments. So let's take a look at what we mean here. Here's our triangle. I'm going to draw an angle bisector. Our angle bisector can be a segment, it can be a line, anything that bisects that angle, so I'm going to extend it there. It doesn't have to just go to the other side. So those two are congruent. That tells us that this is the angle bisector. It's cut this angle in half. I'm going to call this triangle ABC and call this point D. It divides the opposite side into segments. So here are the segments that the opposite side has been divided into. Those are proportional, so that tells me that AD over DC, those are those two pieces. And that is proportional to the two adjacent segments. Well, here are the adjacent segments. This one and that one. And we're going to match these two and those two. So that's going to be proportional to AB over BC. So we make a ratio of those two, make a ratio of those two, and they are equal to each other. So it just gives us a way to set up this proportion. So questions there? So let's take a look at a quick example with this idea, and then we'll be done. Triangle, angle bisector, X 25, 9, and that whole side is 24. And we want to find X. So this is our angle bisector. It divides this side into segments that are proportional to these two segments. So I'm going to write my ratio with X. X over 25 equals, and how am I going to write my other ratio? Which one am I going to match up with X? 9. That's the adjacent piece. And what is the piece that's adjacent to 25 here? How do we figure that out? 24 minus 9. 24 minus 9 is 15. So 9 over 15. Make a proportion, make a ratio with these two pieces. Make a ratio with those two pieces. And we set them equal to each other. So 15x is going to be 225. 9 times 25 is 225. Divide by 15. And we get x equals 15. Questions there? So just another way of setting up proportions. For this section, the side splitter theorem is really the main idea. The side splitter theorem. This is just a little extra that we can add on. Side splitter theorem is the main idea for this section 7. All right, let me put the homework up, and then we'll go over the homework from last time. So there's the homework. Common Core week